This call is now being recorded.
Hello and welcome to another online chemistry review lesson. I'm teacher Michael, and today I would like to start with a few topics to help you get ready for your final exam, for the M4 chemistry exam. Our first topic for today, we'll begin part one of our video. There's going to be two parts, and the first topic will be condensation reaction to make an ester, and we'll also learn the difference between a condensation reaction and an addition reaction. Okay, so we'll look at the two differences there. Here on the screen, you can see we have a condensation reaction to make an ester, and this will involve two reactants, which are going to be an alcohol here on your left, okay, and also a carboxylic acid here on the right. And we're going to have the two structures shown here. So on the top left here is the skeletal structure, which you also need to know for your exam. And we're also going to have the chemical display formula used, which you need to know for your exam. And this will be for a particular structure requirement on the exam when you're asked if you need skeletal or chemical display structure. So ask for skeletal, use this methodology, or this one, this structure. Okay, so we can see an ester is going to require these two reactants, an alcohol and a carboxylic acid. And remember what an alcohol is. What we've learned is that these are going to be organic structures. So there's usually carbon and hydrogen, and here you can see in the structure we've got carbon and hydrogen. And if there is another atom that's not carbon and hydrogen, it must be shown on both structures. In this case, you can see there's oxygen. So oxygen in the red circle here is shown on the chemical display structure here and also on the skeletal structure. All right. Carbons usually don't need to be displayed if you're using a skeletal structure. And so here we can see we have this carbon in the red circle, which is going to be located there. And the second carbon in the second red circle will be located here. And the third carbon in the red circle will be located here. Now, following this pattern, you would think where the red arrow is, there would be another carbon, right? However, since we have an atom there that is not a carbon or hydrogen, but an oxygen, we must denote that there is an oxygen here by writing an O. Okay, so the H afterwards, it's customarily added, and that would be this H right here, just because it's next to an atom, not a carbon. And looking at this, you can see that this is a 3-carbon alcohol, all right? 1, 2, 3 carbons. And also remember the rule, carbon always has 4 bonds, 4 and no more. So if you're looking at this first carbon here, okay, you can see that we have 3 hydrogens. Okay, so 1, 2, 3 in the chemical display structure. So in the skeletal structure, there are also 3 hydrogens. Okay, here where my blue arrow is, you can see 3 hydrogens. I'm writing them down. And these 3 hydrogens do not need to be shown on a skeletal formula structure. However, you can see on the chemical display structure down here, okay, they are added. Sometimes chemical display structures don't have the hydrogens, but it's good to put it, especially when you're learning chemistry, just so you know they're there. And remember, carbon always has 4 bonds. So if you take a look at this first carbon here in the red circle, you're going to notice there are 4 bonds. Okay, and I want to highlight those bonds here with a purple circle, and you can see the 4 bonds, just so you're clear. 1 bond, 2, 3, and 4. Okay, And you can see 3 of the bonds go to the hydrogens, right? And then we got 1 for the carbon next over, okay, which also has 4 bonds. So that means if this carbon here is located here, then there must be 4 bonds. Well, I can see the first bond here, okay, in the red line, okay, is there. And where are the other 3 bonds? Well, they're invisible because they don't need to be shown in the skeletal structure. And we can see that they are right here, but we don't need to write them for the skeletal structure, okay. So if you look at the second carbon, okay, which is the second carbon here in the structure, circled in red, that would correspond to this carbon there. And we can see that it already has 2 bonds, this bond there and this bond here, to connect to the adjacent or carbons next to it, okay? So if there's already 2 bonds, but carbon must always have 4, well, what's 4 minus 2? Well, we need 2 more bonds. So in organic chemistry, it's understood if those bonds aren't being shown, they're not going to be bonds other than hydrogen bonds, okay? So we just put 1 single bond to the hydrogen and another hydrogen, okay? So they're there automatically. And again, you don't need to show those on the skeletal structure, but know that they are there. Okay, so these hydrogens are located right here on the chemical display structure on the bottom. Okay, but they do not need to be shown for the skeletal structure at the top. Okay, all right. And again, the carbons for the skeletal structure will be at the end or at a kink or a angle right here, okay, or where the bend is, or the joint of the lines. So there goes another one, okay. So that's where the carbons are on these skeletal structures. And again, if there was no oxygen here, that would also be a carbon. But since there is an oxygen, we put an O there, and that will automatically tell you there's no carbon there, okay. All right, now to name the structure, count the number of carbons, 1, 2, 3. I don't see any double bonds, all single bonds. So 3 carbons would denote that this is going to be a alcohol that begins with PROP. Okay, so remember, PROP, prop means 3 carbons. And we can see the functional group, OH, that's an alcohol. So that's going to be propanol, okay? So propanol, OL. Now, what if there was no OH here, okay? What if there was just absolutely no H at all, okay, or an O? Well, then it would have 4 carbons, right? 1, 2, 3, 4. And 4 would mean that you would want to use a different prefix, which would be but, B-U-T. And since there is no functional group OH, which denotes alcohol, this is just an alkane, and that would be butane, A-N-E, because there's single bonds. Okay, we'll talk about the differences with the naming, with the different bonds shortly in this video. Okay, all right, so our first reactant is going to be an alcohol, okay? And then we have another reactant over here, the carboxylic acid. And we know this is a carboxylic acid because instead of just an OH, which would mean alcohol, we have another part, this double bonded oxygen, okay? So we can see there's 2 bonds to this oxygen, all right? And don't forget that the structure at the top is the same structure as the one on the bottom, okay? And again, you can see the carbons. We have 1, 2, 3 carbons for the structure at the bottom, and at the top, okay, 3, 4 carbons, okay? And to make this one at the bottom match, we need to put a 4th carbon, okay? Good, so now we have 4 carbons. All right, now, if you want it to be propanoic acid, we need 3, okay? So to correct this, we would simply just remove that carbon now, but then at the top we've got 4 carbons, so we need to remove 1. So count, we have 1 carbon here, 2, and 3. So this should not be there. Okay, so I'm just going to go ahead and remove this. Okay, so we'll just color it with some yellow. Maybe we'll add a little yellow shape here, okay? So I can just put like a little yellow circle here. You can block it out. Okay. Okay. So there we go. Let's just say we've got, now we have 3 carbons. 1, 2, 3, and say here 1, 2, 3. Okay. All right, so if we have 3 carbons, we know we're going to use prop. All right, so down here, circled prop. And since we've got this functional group, which I'm going to circle in the blue, that would be a OH like an alcohol, but with a double bonded oxygen on the same carbon. That's going to be a carboxylic acid. Okay, so that's the name of this functional group, carboxylic acid. So you can see I'm writing it right up here at the top. And the carboxylic acid is denoted again by a carbon with a double bonded oxygen, and also an oxygen and then a hydrogen connected to that. The carbon still has 4 bonds. Okay, so again, you can see 4 bonds, 1, 2, 3, 4. Okay, so that'd be the black lines. And what we want to do is just make sure we have the name correct. All right, and we can see that the name is right here. Okay, prop, meaning 3 carbons, and we have the functional group named in there as well, and that's going to be circled here in red, oic acid. Okay, so that functional group pertains to this part of the molecule. So you need to be able to recognize the functional group. Okay, so it's a carboxylic acid with 3 carbons. That's why we say prop. Okay, prop means 3 carbons. Okay, so propanoic acid would be this particular molecule. Okay, now these 2 substances, an alcohol and carboxylic acid, will undergo a reaction, polymerization reaction. Sometimes if there's going to be carboxylic acid on both sides of the molecule or an alcohol group on both sides of the molecule. But in this case, there's only 1 functional group on each end of the molecule. So for example, there is no alcohol group on the left side, like here. Okay, it's not there. So that will be for polyesters, we'll talk about later. We only have it right here, only 1 functional group on this side and 1 on this side. So that means we're only going to get 1 ester bond created. And an ester bond, if you remember in class, is going to be the carboxylic acid reacting with the alcohol group. And these 2 are going to connect, but in order for that to happen, we need 3 atoms to come out in total from these 2 reactants, and that's going to be H2O. Okay, now which atoms need to come out? Well, if you take a look at the alcohol, okay, the first one that's going to come out for the alcohol is this hydrogen. Okay, so that's going to drop out. So we can just put the H over here. Okay, so the H needs to come out. And then we are going to need the OH, okay, over here. Okay, so this OH group needs to come out as well. Okay, so that's going to give us O with an H. Okay, and when you put that together, okay, so these come out, we're going to have H2O. Okay, so H2O. How do we get H2O? Well, if you look, we've got an H here and an OH. That's H2O. Okay, so when those have been taken out, it means that this part in the black box, all of this does not exist anymore, okay? All of that is gone. So you have just this O connecting over here to this carbon, okay? There's a carbon there, all right? So the H comes from the alcohol, and the carboxylic acid will lose the OH, all right? So that's denoted here at the bottom. We do that. So let's take a look here at the chemical display structure. Might make it a little bit easier. Okay, so again, this H, let's put it in red. This H will come out, and this OH will come out as well. So what happens is this oxygen will connect to that carbon. So just connect, and it'll make a covalent bond. Okay, not an ionic bond, covalent bond, because the oxygen and carbon are nonmetals. So they're going to be sharing electrons. And when you do that, you can see that, let me just put it in purple here so you can identify it a little bit easier. Okay, this oxygen will connect with the carbon. All right, so here you can see that oxygen is connected with the carbon here at the bottom. Okay, so we've connected the two structures. All right, and if you look down here at the bottom, you have the final ester. Notice we have the alcohol, what's left of it, okay, right here. You have a 3-carbon alcohol right here. And we also have the carboxylic acid, okay. So what's left of the alcohols in the black box here, and what's left of the carboxylic acid is right here in the blue box. We still have that double bonded oxygen here, but where's the OH? It came off, okay? And the alcohol lost an H right there that was connected to this oxygen to give you water. And when those have been removed, those 3 atoms to make H2O, you're going to get this bond right here, okay, where this red arrow is I just drew, okay? So that's going to be where it connects. So this is called the ester functional group here in this red square, okay? And that's denoted by, you can see COO, okay? So sometimes you'll see it written COO like this, all right, in a condensed molecular formula, all right, COO. And if we still have the carboxylic acid, there would be an H at the end, COOH, right? Okay. So that's our ester. It's been connected. We have the ester group there. And once we have the ester, just don't forget the second product, which you should also know for the exam, is going to be water. Okay, so water did come out. All right, H2O. 1 hydrogen came from the alcohol, and the second hydrogen, along with the oxygen, came from the carboxylic acid. All right. Now, if we take a look at how to name this ester, we can see that we have the alcohol is going to be used in the naming portion first. Okay, so here we have propyl. Okay, so propyl comes from the alcohol naming. So we can see propanol. So propanol was used, so we use propyl. Keep the same PROP, meaning 3 carbons, but instead of OL, it's going to be replaced with YL, okay? So that means it's no longer an alcohol. It's an alcohol that's lost a hydrogen atom, all right? And then we have in the blue circle here, the conjugate base of the acid, which means the acid's lost its acidic properties. And so the propanoic acid will be renamed to propanoate, okay? So if you put the two together, that will give you the name of the ester, propyl propanoate, okay? So you can imagine if the acid were 2 carbons, it would be eth, ETH, instead of prop, it would be ethanoic acid. So then this ester would then be called propyl ethanoate if the acid we used had 2 carbons here instead of 3, okay? So remember, the first part of the name comes from the alcohol, and the second part of the name comes from the carboxylic acid, okay? All right, so that's how you make an ester, how you name an ester, using an alcohol and using a carboxylic acid with different number of carbons. And this particular reaction, again, is called a condensation reaction because condensation means the state of matter change from water vapor to liquid, okay? So we're basically removing water here, okay? So the water is down here. And this reaction can also be referred to as, and this can be helpful on your exam, as a dehydration synthesis reaction. Okay, dehydration. Synthesis and dehydration means to remove water. So that's what we're doing in this reaction. And synthesis means to make. So we are removing water to make an ester. Okay. So again, removing water, dehydration, to make an ester, make or synthesis, synthesize, meaning to make, all right? So hopefully that was clear and helps you out a little bit with understanding how we make an ester and how we name it using alcohols and carboxylic acids. Okay. And let's take a look at this particular slide. And this we've seen before. What happens when we have an alcohol group and a carboxylic acid group on both sides of the molecule, not just one side? Well, that will allow you to make an ester link or ester functional group on both sides of each molecule. And then you can have a very long chain. Okay, so we've recently done this in class, but as a review, let's take a look here. We can see that we have in the black circle, all right, we have this red rectangle, and in this black circle, second one, we have a blue rectangle. And this just denotes, and you'll see this on the exam, that it could be any number of carbons in there, okay? It could be 0, 1, 2, or 3, 4, 20. It doesn't matter because we're going to just abbreviate it to make it a box. And then what you do have is, for example, here, you have the, if you look at the first black circle, okay, on the left side, okay, in this black rectangle on the left, that is the carboxylic acid functional group, right? So we talked about the COOH, okay, so we can see that COOH inside there. 1 carbon, 2 oxygens, and a hydrogen. And we also have it on the right side of the black circle. So I put that in another black rectangle here. And that's going to be COOH as well. So that's another carboxylic acid functional group. So we have one on both sides of this black circle. So we call this a dicarboxylic acid, as we've reviewed in class. Okay. So this will allow this dicarboxylic acid to create an ester link on this left and right side. And then if we look here at this alcohol, okay, this is a diol or dialcohol, okay? So we can say diol, D-I-O-L. I'll write it a little bit more clear for you. So Di meaning 2, okay? Like Bi, bicycle, 2 wheels. Bi is used sometimes to denote 2, or in this case in science and other fields of study, we also might use Di instead of Bi. So di means 2, and then all is shorthand for alcohol, okay, or we can say dialcohol. Okay, so diol is also a dialcohol, okay? All right, and don't forget that a alcohol group here, circled in the red circle here, a carbon connected to an OH, that's an alcohol. And then we've got one again on the right side that is going to be another alcohol group. Okay. And notice it's on both sides of this molecule, and that molecule is represented here in the in the blue rectangle. Okay, so we've got alcohol group on the left and right side. So again, this allows this particular molecule, a diol or dialcohol, to create an ester bond on both sides, left and right, just like the dicarboxylic acid, okay? So for this would be a carboxylic acid, okay? And yeah, this is a Y right here. Okay, so a dicarboxylic acid, again, you've got one on the left and and one on the right. So just recognize the functional group, okay? And here you can see an alcohol group on the right looks different than a carboxylic acid group on the left. So these are the two primary functional groups you should know for an ester. Okay, so we talked about the ester losing the OH and the alcohol losing the H here. So I just crossed them out with a black X, and they're going to connect. So what connects, again, is going to be the oxygen here will connect to that carbon, and that's going to create an ester link. Okay, so if we look right here, we can see that I've denoted that in this purple oval at the bottom. We have the ester, okay? Functional group, C, double bonded oxygen with an O. And notice that the double bonded oxygens from the carboxylic acid and the blue oxygens from the alcohol on the right. Okay, so I use the color so you can see the difference. Hopefully that helps you to see the separation of structures. And again, what did we remove? We removed H2O. Okay, one hydrogen from the alcohol, another hydrogen from the carboxylic acid, and the oxygens from the carboxylic acid here for the water. Okay, so removing the water, again, dehydration synthesis or condensation, polymerization. And we say polymerization because we are making a polymer here because we have more than 2 or 3 monomers connected. So here you can see we've got the dicarboxylic acid monomer, the diol or dialcohol monomer, and that gets connected again with another dicarboxylic acid, which we haven't made the ester link yet, and another diol or dialcohol monomer. Okay, so we haven't made the ester link there. Okay, but you guys did in your classwork where we had worked on this. Okay, so hopefully that gives you a little bit better understanding. And if we just want to go into detail one more time very quickly, you can see we're going to make the ester link here, which we haven't done yet because we got the plus sign. All right, you're going to again lose this. Well, let's just do this. This hydrogen will come down, and this oxygen will come down, and this hydrogen will come down. When I mean come down, it's going to be removed. Okay, so the carboxylic acid will lose OH, the alcohol will lose the H there. So those are no longer connected. Okay, sorry there. Just that. Okay, and this means this oxygen can connect to that carbon now. All right, so there should be basically like a line connecting that oxygen to carbon once they make the ester link. And down here, this will be your H2O. It's removed. Okay, so hopefully that's giving you a little bit of a better understanding for condensation polymerization. Okay, so again, condensation polymerization is how we make a polyester. Remember, poly meaning many, ester, so many ester links, right? So we've got the ester link right here, C double bond O, O, and we just keep on doing it. Then we do it over here, okay? And here you can see on this side, the double bonded oxygen will be on the right side, and then this one's on the left side of the ester link. It doesn't matter. It's still a carbon, double bonded oxygen connected to another oxygen. Okay. All right, so again, dicarboxylic acid is a monomer, and diol is also a monomer or dialcohol. All right, and you can see there is a red rectangle representing the acid and a green rectangle to represent the alcohol. Okay, so up here, so to have 2 different monomers for condensation polymerization, you can see how polyester is created: red, green, red, green, red, green, 2 different monomers, and these are the 2 different monomers just alternating in connection. So acid, alcohol, okay? And you can keep on doing that as long as they have the functional group on both sides of the molecule. All right, so that's how we make polyester. Remember, polyester is used for shirts, bags, maybe car seats, many different fabrics, maybe for camping gear, all right, or maybe for making tents. So nylon is also used, and that's a different material. Okay, but polyester is fairly inexpensive and easy to make. Okay, so that should be a nice review lesson for you guys for condensation polymerization. Okay. All right, what I want to go into, we're going to come back to this slide here, is comparing condensation polymerization to addition polymerization. Okay, so addition polymerization, instead of condensation polymerization, we're not going to be removing water. Okay, so addition polymerization, as you can see the term here, is going to be when you have a carbon-to-carbon double bond, okay, as a monomer. So in this case, you can see it's ethene. Okay, we say ethene because there's two carbons, ETH, right? And we say ENE because there's a double bond, all right? And we have another ethene monomer and another ethene monomer. And if we take a look at the carbon, okay, let's see, how many bonds can we count? Okay, so we can see that we have a double bond there. So that means this carbon on the left and this carbon on the right have two bonds from that. And then the carbon on the left has another bond to this hydrogen and another one there to that hydrogen. So that's a total of 4 bonds. And then the carbon on the right, again, has the double bond in the middle, but also has a bond to the hydrogen on the right and a hydrogen at the bottom on the right. So that's 4 bonds for that carbon. So carbon has 4 bonds, and there's no way that you can make this ethene, okay, which is this whole structure and okay, in the red circle here, connect to another structure because it already has 4 bonds. So in order to make a bond, let's say you want to connect these 2 ethene monomers here, okay, you can't do it because that would give carbon 5 bonds, okay? So that means we need to remove this bond and also that bond. If we remove it, carbon will have 3 bonds, and then we can use the 4th bond space to connect these 2 structures, okay? And in doing that, that would allow you to continually connect many of these monomers together, okay? And so you can see that is going to be done in this example. We've got 3 monomers, ethene, and the double bonds will be broken, and then we can create monomers with only 3 bonds, and they will connect, okay? So once they connect, the structures will look like this down here, okay? So you can see this is going to be 3 monomers, right? Because each monomer, a single unit, has 2 carbons. So here we can see 2 carbons there, okay? And I can see 2 carbons here. Okay. And then the second monomer, 2 carbons, and here the second monomer is 2 carbons. Then the third monomer is also 2 carbons, and then that's identified right here. Okay, so if on the exam I ask you, say, to draw a ethene polymer, which would be known as polyethylene, for example, okay, you would need to figure out how many monomers, okay? So usually you might be asked, can you create a polyethylene polymer with 3 monomers, and then it would look like this down here at the bottom, okay? If they're connected, it's a polymer. But if they're not connected, then it's just a monomer, okay? And then if the double bonds are there, it would look like that at the top, okay? So we have ethene monomers, and then here, this is not ethene anymore, okay? These are in transition. They're going to connect to each other, okay? So once they connect, it looks like that. All right, so this would be a polyethylene with 3, made from 3 ethene monomers, okay? So that's addition polymerization. And again, if you also wanted to show 3 monomers, but you didn't want to draw 3 when you made the polymer, okay, you can see where we have the letter N. This can be replaced with a number, so 3 of those. and then the N here could be replaced with a 3. So that's letting you know that it was 3 of these monomers to give you a polymer that's as long as 3 of those connected, like you see right here in the black rectangle at the top here. Okay, so the black square and rectangle, those two structures mean the same thing. Okay, right there. Okay, so again, this is polymerization, but it's not condensation polymerization, it is addition polymerization, okay? And there is no water produced for this type of polymerization, so that's why we don't say condensation. We're just adding something simply, adding another monomer, and then another monomer, and then another monomer, okay, to create a very long polymer, okay? All right, so let's take a look at another monomer and another polymer in that case, okay? So in this case here, we have the polymer known as polystyrene, okay? So this particular monomer, we have how many monomers? Well, let's see. In this case, we have what looks like an ethene molecule because we've got 2 carbons, okay? And we've got our 3 hydrogens. But instead of a 4th hydrogen here, we have a ring structure added to it, okay? So this would be a benzene ring, and it's added instead of a hydrogen. So this monomer, still being 2 carbons, would just be depicted in this red rectangle here, okay? And then we have another one right there, okay? So you can see that knowing this, you can count how many monomers were used to make this polymer, okay, of polystyrene. And why do we say polystyrene? Well, poly means many, okay, many styrene monomers. So this is a styrene monomer, okay, styrene monomer, okay. So monomer means just one unit, and you can see I've got a monomer and one red rectangle, another monomer, and the next red rectangle, and then we can just keep going. So how many monomers? 3, 4, 5, 6. Okay, so we use 6 styrene monomers to make this polystyrene molecule. They'll be connected. So what does the monomer look like? Well, remember the monomer is going to need to have a double bond. Okay, so maybe we can just take a look here on the right side. Okay, so on the right side here, we have an abbreviation. Okay, so if we have, say, the number 6 here, that's telling you we've got 6 of these monomers, okay, to create the polymer. And the full picture would be on the left side here, as we saw. Okay, so we take a look here. We have 6 monomers, right? So 1, 2, 3, 4, 5, 6. And then the monomer is also represented, 6 monomers, by putting a number 6 here where this N is. Okay, just put a 6 there instead of the N. And then if you show it inside of brackets like this, it means you are telling me that 6 monomers have lost their double bond to connect to make this structure on the left, okay, which is polystyrene. So the styrene monomer, okay, would be just like this, but there would be a double bond here, okay? And then this would be gone. Okay, so we can denote that. Okay, so a styrene monomer, okay, we would get rid of the bracket. Okay, we would also get rid of that connecting bond. Okay, and so that's a styrene monomer. Okay, and then you got to remember carbon has 4 bonds, and you can see that this carbon has 4 bonds. Okay, again, where are they? 1, 2, 3, 4. Okay, and then the carbon on the right has 4 bonds as well. 1, 2, 3, 4. Okay, so that is the full monomer of styrene. So if we're going to connect it, we need to remove the bond there. Now carbon has 3 bonds, and that allows space for it to connect, and that's what happens when we make polystyrene. Okay, so polystyrene again can be just denoted with the brackets and the letter N, and the N represents the number of how many monomers you use to make the polymer. Okay, so polystyrene. All right, so keep an eye out for that on your exam, how to connect monomers. And remember, polystyrene is the material used for styrofoam, right? So styrofoam is used for styrofoam cups, bowls, plates, and packaging material, say for TVs or speakers. Okay, so very commonly used polymer, polystyrene. Okay, and polyethylene is used for water bottles and plastic bags. Okay, all right. So again, just a little review, the difference between addition and condensation polymerization. Polyethylene on the left is an addition polymerization process because we're just adding on other monomers that are the same. You only need one type of monomer, and you don't make any other substances when you connect the monomers. You're just adding and adding and adding, but you do need to have a carbon-to-carbon double bond first. Okay, you need to have a double bond. In addition, polymerization process will not work if you don't have a double bond first between these carbons, okay? So again, I mean, there needs to be a double bond here. So if you break that bond or remove it, then we can connect it with other like monomers. That's addition polymerization, and here you can see we've got the ester functional group, and this would represent condensation polymerization. And you can see that the ester functional group is shown right here. Okay, and remember the R just means a carbon with another part of the molecule. So it could be 2 carbons, it could be 3, it could be 4, whatever it might be. Okay, so that's what the R stands for. So it's carbon with a double bonded oxygen and a single bonded oxygen. That would be an ester bond. And then over here on the left, that would be another carbon, and then the rest of that structure, which could be 2 or 3 carbons. Okay. All right. All right, so let's do a little review of an organic chemistry skeletal structure. What would be the name of this structure? Okay, so this skeletal structure is a little interesting because we've gone over skeletal structures, but we didn't really show the carbons. But that shouldn't change how you name it. So taking a look here, we can see that we need to count the carbons first. Okay, so on the left, I know there's a carbon here. If it's not a carbon, we should have another letter from the periodic table, okay, or symbol to mean that it's a different atom. Okay, so if it said like a N for nitrogen or O for oxygen, that would be there. But since there is not the N or O or anything, it's just a carbon. And in this case, there's a letter, but it's C, right? The C here, which just means carbon. Does the C need to be there? No, but sometimes you do see that in skeletal structure formulas. Okay, so we got 1 carbon there in the red circle. We'll start on the left. We've got another carbon here. Okay, then we have another carbon there, a 3rd carbon, and the 4th carbon's here. 5th carbon, 6 carbons, and then a 7th carbon. Okay, so we've got 7 carbons here. Remember, all carbons need to have 4 bonds. Not too important for skeletal structures. Since the carbon here on the left side is at the end and it has 1 bond right here, there's room for 3 more bonds. And since it's not shown sometimes, you just know that they're going to be and can only be hydrogens. In this case, it's telling you 3 hydrogens. Okay, CH3, or in this case, they've got H3C. Okay, and what that is really telling you is the carbon is at the end and it's got 3 hydrogens like this, okay? So that's what the CH3 means. And same thing on the right side here, okay? There's just carbon with 3 hydrogens, okay? Okay, so let's go and name this particular organic compound. So step 1, count the number of carbons. So we have 1, 2, 3, 4, 5, 6. Okay, then we have one more, 7 carbons. We got a total of 7 carbons here in a chain. So we need to have the prefix or the naming structure for 7 carbons. Okay, we know 6 would be hex, H-E-X, right? Because we know like a hexagon has 6 sides. But for 7 carbons, we're going to use the prefix hept, H-E-P-T, okay? So hex would mean 6, hept would mean 7. So we're going to use 7 here, okay? So we're going to use H-E-P-T to start off with, okay? Now, for the second part of the name, we need to look at the functional group, okay? Now, if we didn't have anything else, just this line here at the bottom, then it would just be heptane. But in this case, we do have a functional group. It's right here, okay? Just a double bonded oxygen, nothing else on the carbon. Is going to be known as a ketone group, so K-E-T-O-N-E, ketone. And we're going to use only O-N-E, the N part of that, and just add it to the name. Okay. Heptone. Okay. But we're saying heptane, right? So we're going to make sure that we have, let's go back. Make sure we're very thorough. So instead of that, we need to say heptane, all right? But we're going to move the E here, then put the O-N-E, heptanone. Okay. So it had 6 carbons, it would say hexanone. And this is heptanone. Now, we're almost done. Interestingly, if we count from the left, this would be carbon 1, this would be 2, and this would be carbon 3. So we can see the functional group, the ketone group, is on the 3rd carbon. So that means we need to put 3 in front with this hyphen here, 3-heptanone. So now I can read the name and the red square, 3-heptanone, and know that this ketone group is on the 3rd carbon, okay? So if you counted from the right, okay, for example, not the left, it would be 1, 2, 3, 4. It'd be on the 5th carbon. And then there would be 5th or 5-heptanone, right? And we don't do 5-heptanone because we're going to use the lowest number, okay? 3 is lower than 5, so we don't say 5-heptanone. It's going to be 3-heptanone. So you count from left and right, from the left and from the right, whichever one gives you the lowest number, that's the number you use, okay? So that's 3-heptanone. Okay, hep from the 7 carbons, O-N-E meaning ketone functional group, and carbon 3, that's where the functional group for the ketone is found, okay? All right, so keep that in mind. And what if we had a carbon-to-carbon double bond, okay? So let's say, for example, we didn't even have this functional group here, okay? Let's say it was just this, heptane. But we had a double bond right here, okay? So there's a double bond here, okay? So again, count the number of carbons, 1, 2, 3, okay? And then we've got 4, a 5, 6, then we got one more, a 7. Okay, so 7 carbons, but is this heptane? No, because we have a functional group here, and that's the double bond, okay? So carbon 1 and 2, you're going to see that's where on carbon 2 the double bond begins. Okay, remember one bond is right here and the other one's on the other side. So instead of using A-N-E, okay, this will be called heptene. Okay, so heptene, E-N-E, right? And then that's found on carbon 2, so we're going to say 2-heptene. Okay, double bond is on carbon 2. All right. And if we didn't have a double bond at all here, okay, if we didn't have a double bond, then it would not be heptene anymore, and we wouldn't need the 2. Okay, what would we call it? Well, it's just 7 carbons. We would just call it heptane. Okay. All right, and then what if we had 3 carbons? Okay, let's take a look at that. So let's go ahead and compare the alkanes, alkenes, and alkynes real quick. Okay. All right, so here you can see we have the naming structure. Don't forget carbon always has 4 bonds. All right, so we've got the carbon, okay, with the alkane too. This alkene, we've got 2 carbons, and the alkyne, we have 2 carbons as well. So I put it there with the yellow C, so you can see it. And then the hydrogens are in red, okay. The red atoms right there are all hydrogens, okay. Okay, so what's the difference again between an alkane, an alkene, and alkyne when comparing these? Is the more bonds you have, okay, the more reactive and unstable the molecule is going to be. So 1 bond between the carbons, here you can see in the red circle, that's going to be A and E. If you don't see a double or triple, only single, that's going to be an alkane of sorts, right? So like ethane, propane, butane, okay? But if you even see even 1 double bond, okay, it becomes an alkene. And you need to show where this alkene is by putting the number. Now, since this is just 2 carbons and we have a double bond in between, we say ENE, alkene, right here, okay? And that is going to be, again, denoted by ENE in the name. And this one here, 3 carbons, YNE, and alkyne, okay? So how would you name it? Count the number of carbons, okay? So this one, 2 carbons, single bond, this would be ethane. Okay, remember ETH is used for 2 carbons, ethane. Then this has a double bond, so we're going to say ethene. Okay, so this is ethene. All right, and since this one here has 3 carbons, we're going to say ethyne. All right, just know how we change the name here, ethyne. Now notice the number of hydrogens change because of the rule. Carbon always has 4 bonds. So ethane here, I can see there's 4 bonds around the carbon. 1, 2, 3, and 4. Okay, for all of them. So if there's only a single bond in the middle, that means the carbon on the left has room for 3 more bonds, and we're going to only put hydrogens there. Okay, we can't put anything else, or it'll change the molecule. It won't be an alkane. All right. And then here on the next example, since the carbon has 2 bonds already, both carbons, right? That only leaves room for 2 more bonds for each carbon, so we can only add 2 hydrogens, okay? And then if we look here on the right side, alkyne with 3 bonds, well, that's going to cause carbon to only have room for 1 more, so we can only add 1 hydrogen for each carbon, okay? All right, so what do we know? Ethane is going to have 6 hydrogens, ethene can have 4 hydrogens, and alkyne can only have 2 hydrogens. So think about this because you might be tested on that concept for the final exam. Okay, let's take a look here at one last key point that you should know for the exam is when you have a double bonded carbon, you can get those created from a single bond between the carbons through a process known as cracking, okay? So in this case, you can see we have ethane, okay, is going to be combined with high temperature and some steam, and that's going to cause hydrogen to come off on both sides. So we'll go from 6 hydrogens to 4, and that will allow a double bond to be created. Carbon always needs 4 bonds, and then you get ethene, okay? So ethene and these double bonded hydrocarbons do not exist in oil. So if you want to make ethene, you need to get the ethane from the oil, for example, okay, or propene or butene. And cracking allows you to do that. And then you can actually add many of these. Remember, many ethene monomers can be added together using addition polymerization to make polyethylene, right, for plastic bottles and plastic bags. And of course, in this case, when you crack, your product is hydrogen gas, not water, okay? That's cracking. And then once you have this ethene, okay, something interesting is you can go back to ethane, all right? Or you can use the ethene, add some water, an acid catalyst with heat, and make ethanol, okay? So we can make alcohol from ethene using an acid catalyst. Okay, so again, remember, a catalyst is a substance used in a reaction that's not going to be consumed. It's just there, but it won't be used up, okay? So heat and acid, for example, can turn ethene into an ethanol, okay, or an alkene to an alcohol. So keep that in mind, all right? So this is found on page 214 in your textbook if you want to review this concept a little bit more. Okay, and I want to go very quickly over the fractional distillation column. All right, the bubble caps. So how do bubble caps work in fractional distillation column? How it's going to work is, remember, we're going to heat up the oil at the refinery, about 400 degrees Celsius, and the shorter carbon molecules, okay, will be allowed to, in its vapor form, okay, will be allowed to rise up through the bubble caps, okay? So the bubble cap here you can see is in yellow, okay? So I was going to draw it here so you can see it. So the gas, for example, diesel, okay, since it will be heated up, turn into a vapor, will rise until it gets high enough away from the heat to cool down, to go back from a vapor to a liquid form. And in doing so, it'll cool down and become liquid, and it'll collect on the trays here. And then we can collect diesel fuel, okay? So diesel is about 15 carbons, and we can do this for all the different length of hydrocarbons, right? So kerosene would cool off above here at the top at 170, or less than 170. So diesel here less than 270. So how does the bubble cap work? The bubble cap, you can see in the yellow, allows a gas to come and rise past it, but when it cools down to a liquid, the trays next to the bubble cap, okay, so the tray here looks like the bubble cap, but it's upside down, will collect the liquid, okay, and then it can't fall down any further, and this can be used for every fraction, okay, and remember, the only fractions that are not collected as a liquid would be the gases with 1, 2, 3, and 4 carbons. That would be methane, ethane, propane, and butane. They stay a gas and they rise out through the top of the fractional distillation column, known as refinery gas. Okay. All right. So again, don't forget the properties of large and small molecules, and you can see them on the left here. So make sure to review these in your Google Classroom slides. Okay, so hopefully you did find this review useful. And again, don't forget how the fractional reserve column and the bubble caps work inside for separating the different fractions of petroleum into its different parts. Okay, like so we got fuel oil, lubricating oil, kerosene, also known as paraffin, sometimes used for jet fuel. Okay, and naphtha, very important for plastic uses. Okay. When you're studying for your exam. Okay, so if you have any questions, please feel free to send me a message in line and I'll answer those for you. Hopefully this review was useful, and if you made it to the end of the video, thank you very much for paying attention, and I hope you good luck on your exam and happy studying, and I will see you next time. Again, this is Teacher Michael, and if you have any questions, again, feel free to send me a message. Bye now.